Today we will be discussing the naming and formulas of binary ionic compounds. And don't panic when you see this word binary, because it just means that there are two of them. So don't panic when you see this binary word. Alright, so we're going to break these. Well, before we even do this, let's keep in mind that binary ionic compounds always form between a metal ion and a non-metal. And you're probably saying, well, how do we know what those are? And that's an easy one to answer, because metals always show up on the left side of the periodic table and nonmetals on the right side. And for the most part, we will ignore the metalloids, but be careful, because there are some that are going to show up quite often. Aluminum and arsenic, for example, silicon and antimony, that are very clearly on one side or the other of this demarcation line. So be careful. The way we're going to treat this in this class is, if it is on the left side of this flight of stairs, you can see it here in yellow, it is a metal. So we're not really going to worry too much about metalloids, that distinction. If it's on the right side of this demarcation line, it is a nonmetal. So before we start, we're going to find 3 lists on the back of your periodic table that are 100% necessary, unless you want to commit these to memory, and I don't think you do. The first one is this one. These are all the elements that we're going to call main group elements. That means they are not in the middle section, the transition metal section. So we are going to be paying attention quite a bit to these guys. These can be found in group 1, that's these guys. Group 2, our new numbering system involving the system that we used way back in Chapter 5 and 6 for picking valence electrons. This is now group 3. This is going to be group 7 or 17, depending on how you look at it. 6 and 16, this is now group 5 and 15. I'll let you guys figure out what's going on with carbon and silicon, but we're not going to worry about that at the moment. Alright, so that's one table that we're going to want to be paying attention to. Here's another one. Right below that, you'll find this list. It is highlighted by the fact that it says that we have some D block elements. That's these guys. D blocks are also what we call transition metals. And these do some interesting things. Be paying attention, because if you'll notice that some of these elements, for example, vanadium, can form multiple charges. It exists here in this column, 2+. It also exists in this column here, forming a charge of 3+, and here, forming a charge of 4+. And that is the key for transition metals. And let's keep that in mind, that transition metals can form multiple charges. And it's worth mentioning that these are only some, not all. So by no means is this a comprehensive list. And the last list that we're going to be needing can be found here. These are called polyatomic ions. And this is a pretty long list. And there are some similarities, so be careful, because we've got nitrate and nitrite, We've got sulfate and sulfite, carbonate, carbonite. Quite a lot of different ions going on here. So be careful and keep this list handy. So for the purposes of this course, we're going to break our ionic compounds into two categories. Type 1, and these are just simple ions that do not form multiple charges. They can be polyatomic, but their charges are always the same. So we'll simply say simple ions with one charge. And of course, you can probably deduce that that means that any time we have a type 2 ionic compound, those are going to involve transition metals with multiple charges. And we're going to want to keep in mind these multiple charges because they form different compounds. So let's take these type 1 stuff first, and let's do our simplest. First off, with ionic compounds, there are no prefixes. So ignore that mono, di, tri stuff that we were using for molecular compounds. So a simple ionic compound that is a type 1 is something called sodium chloride. So there's no mono this or that. So all we do is drop the ending off the chlorine and simply name it as sodium chloride. Nothing fancy. If we were going to try something a little bit more complicated, this is called calcium chloride. All right, if we start involving something, say for example, like a polyatomic ion, and we had something that looks like this, remember, these are binary compounds. There's only two ions involved. One will be positive and one will be negative. And so there's nothing tricky about this one. You'll need to look up the name of this polyatomic ion, but that's what this list is for. So if you're looking for a polyatomic ion that looks like PO4, you'll find it right here. So if we're trying to write the name of this compound, there are no prefixes involved. It's simply aluminum phosphate. And that's as difficult as it gets as far as naming. Now, writing the formulas is a bit trickier. Let me show you what I'm talking about. So here we go. Write the formula for writing formulas for type 1 binary ionic compounds. Remember, if it's a type 1 compound, it does not involve a transition metal. So here's a type of question you could expect me to ask you. So write the formula for strontium iodide. We know strontium iodide is going to involve strontium, and we know it's going to involve iodine. What we need is the charges. So this list of ions tells you the charges on most of these single charge ions we'll be working with. So for example, you know from looking at this list that strontium has a charge of +2, and iodine, here it's called iodide because it's an ion, has a charge of -1. So let's put these together. So here is our two elements, and we know that strontium has a charge of 2+, and iodine has a charge of -1. We need these charges to balance out. The overall charge has to be 0. So we could play around with multiplying by stuff and how many with this or that do we need, but an easier way is what we call the drop and swap. This is an easy way to find out how many of each ion we need to make the molecule's charge overall be 0. So if I drop my charge of -1 down here, get rid of the sign because we're just trying to find out how many of each atom there are, and do the same with our strontium, that means that our formula is going to be strontium 1 iodine 2. But we typically don't worry about things that have a 1 next to them. And so our formula for strontium iodide looks like that. Just that easy. Okay, let's try one that's got a polyatomic ion. So here's a question that you can expect me to ask involving one of those. So here's a question you could expect to be asked. Write the formula for something called barium arsenate. Okay, well, here's a hint. If it ends in 8 or 8, it's probably a polyatomic ion. So I'm going to look for my lists and see if I can find both of these. So let's check out barium first. And barium is right here. Barium's right in the middle of group 2. That means barium's got a charge of 2+, so we'll label this with a charge of 2+, so we don't forget this is barium with a charge of 2+. Well, because it ends in ATE, arsenate is a polyatomic ion, so let's go look for it. And I see it right here. Arsenate looks like this. Oops. It is AsO4 with a charge of -3, and we can find it right there easily enough on our list, arsenate. So let's put this together. It's got a charge of -3. Oops, lost my place. So barium arsenate, the arsenate looks like this, AsO4, and it is a polyatomic ion with a charge of -3. So what I'm going to do is I'm going to put this parentheses around it to indicate that this -3 pertains to this entire ion. So not just one atom. And we treat these polyatomic ions like single ions. We never mess with the formula inside the parentheses. So let's try this drop and swap technique. So we're going to drop the charges off, obviously. So we'll put 2 here and 3 here. And we're going to use these parentheses to keep the internals of this polyatomic ion separate. So what's the formula for barium arsenate? And it looks like this. There are, according to this formula, 3 bariums and 2 arsenates in this molecule, and you'll probably be able to figure out that 3 bariums, each with a charge of 2+, easily cancels out 2 arsenates, each with a charge of 3-. So let's take a look at what we're going to call type 2 binary ionic compounds, and these involve a transition metal, which can form multiple charges. So it's not much different, we just need to be a little bit more careful, and we're going to indicate our charge with Roman numerals. So how do we know that we are dealing with a transition metal? Easy. They come from the D block, and it tells us this right here in this table. It says some D block elements. There are a couple like lead that are not quite in the D block, but they still do it, and you'll see here that there's lead 2 and lead 4. But these Roman numerals are what tell us the charge. So vanadium with a charge of 2+ has a little Roman numeral 2 after it. This is by no means a comprehensive list, and be careful because there are a couple that only appear once. For example, zinc, even though it's in the D block, it only appears once, so it doesn't really have multiple charges. Let's try one of these. So here's one. Write the formula for vanadium 4 nitrate. Vanadium is in the D block, and we see it here in our list. Vanadium 4, right there. That tells us that this version of vanadium has a charge of 4+. So let's write our formula for this one. And so we're going to say, all right, we know that our vanadium has a charge of +4. Nitrate is a polyatomic ion. We see it right here. And this is our nitrate. We see it right here. It is in this group that has a charge of -1. And we'll keep that set of parentheses around it to kind of keep it inclusive. And so nitrate looks like this. Sorry. NO3. We'll keep our parentheses around it. It has a charge of -1. So let's do our drop and swap. We're going to take our +4. We'll drop the charges and put it down here. We'll take our -1. We'll drop the charge and put it down here. So our formula is V1NO3 4. But we don't need the 1. It's superfluous. And so our answer for vanadium 4 nitrate looks like this. Now what if we were going the other way? Here's one where we're going in the opposite direction, where it says, name the following type 2 ionic compound. So clearly what's going on here is we have a compound that has 3 lead atoms and 4 phosphate ions. Phosphate is this polyatomic ion. You see it right here in our list of polyatomic ions because it ends in ATE. So you know that's what it is. And it has a charge of -3. We see that here. So if we know coming into this that this phosphate has to have a charge of -3, and there are 4 of them. There's a couple ways that we could do this. We could say, okay, there are 4 of these, and they each have a charge of -3. So what does the charge on the lead have to be to balance this out? Well, of course, it would have to be 4. And that's certainly one way of doing it. Another way of doing it is what we call the reverse drop and swap, where we simply say, this is going to be the charge on this ion, and this is going to be the charge on this ion. And so that makes this lead with a charge of +4, and so we'll say lead 4 phosphate. There are some people that like to include parentheses around their Roman numerals, but I don't really think that's necessary because we're already putting parentheses around our polyatomic ions. So there you go. Naming ionic compounds, both type 1 and type 2, involving single charge ions, transition metals, and polyatomic ions. All right, see you on the next one.